Chemical Nomenclature, Part 2, looking at covalent and acid-salt nomenclature. Covalent compounds are those compounds which form between elements that have low differences in electronegativity, so they tend to be close together on the periodic table. Generally, they'll be two or more nonmetals, but they don't have to be. There can actually be metals which form covalent compounds. The covalent compound, unlike the ionic compound, will form an actual covalent bond. This is sharing of electrons rather than a transfer of electrons. This then forms discrete molecules rather than networks of ions like the ionic compound does. An example is CO2. The CO2 molecule is a free molecule which is able to move around on its own without interaction with other compounds, if it wants to. The properties of covalent compounds are typically low in their melting point, especially versus ionic compounds, which tend to be very high melting point. They tend to be electrically insulating, which means they don't conduct electricity very well generally. They usually do not ionize in water, which means they will not form ions splitting apart, with the exception of acids. And they have a wide range of physical properties at room temperature, ranging from solids to gases in a similar way to what nonmetals do. Generally, our covalent substances will be soluble in nonpolar solvents, although there are some polar covalent substances which are soluble in nonpolar and in polar, or even only in polar. The nomenclature of covalent substances depends upon the type. So we're looking at, again, like ionic substances, the type and number of elements in the covalent substance. For covalents, there are generally binary covalent compounds, which are a lot of the covalents we deal with. And then we also have acids. Those are the two basic categories of covalent nomenclature. The big exception to this is organic compounds, but we're not really going to talk about organic compounds at this point. If a compound is made of two different elements, it is, just like the ionic, a binary system. If it is made of three or more elements, it's a ternary system. As far as covalent substances are concerned, this is generally only with acids. Binary covalent nomenclature is written with the more metallic nonmetal before the less metallic nonmetal. For example, carbon dioxide. Carbon is more metallic than oxygen is, so it's written first. The thing that is closest to the metals, from greatest to least, carbon to fluorine, in this series of common covalent substances, as you see here. The nomenclature system for binary covalent compounds is naming the more metallic name first, and the less metallic root with the suffix IDE second. We also will insert a prefix before the name of both elements to indicate how many atoms of each element there are in the compound. If the element has only one atom in the compound, and it is the first element in the compound, the prefix mono, which is what would be used for the only one atom of the element, is omitted. For example, we have carbon dioxide. CO2, we have one carbon, two oxygens. The carbon atom, being only one, would have been monocarbon dioxide, but because carbon is first, we omit mono. We do not use mono in the first element of the compound. If the name of the prefix ends with either an A or an O, it is dropped preceding an element that's name starts with O. So generally this will just be oxygen. The example of this, As4O6, is tetraarsenic hexoxide. As4 is a compound with 4 arsenic atoms. The prefix for 4 is tetra. O6 has 6 oxygens. The prefix for 6 is hexa. Because the hexa precedes oxygen with an O, the last A is dropped. So instead of hexaoxide, it's hexoxide. The prefixes that we use follow Greek order: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca, undeca, dodeca, so on and so forth. Naming acids, to understand nomenclature of acids, we have to understand what an acid is. An acid is something that is formed from hydrogen bonded to either a nonmetal of generally group 6 or 7, that is excluding oxygen because that would form water, which is, well, technically an acid, not considered in this concept. And these will form what we call binary acids. Something like HCl is a binary acid, hydrogen bonded to chlorine, and this is hydrochloric acid. The other way that we can get acids is from hydrogen bonded to our polyatomic ions, the ternary acids. Generally, these will be oxyanions, although they don't have to be, because we can have things like hydrogen cyanide as an acid as well. An example of this is hydrogen bonding onto carbonate. This forms carbonic acid. The acid will be named as an ionic substance unless it is dissolved in solution, aka it is in water. So HCl would be named hydrogen chloride unless it is dissolved in water, in which case it's then hydrochloric acid. H2CO3 would be hydrogen carbonate unless dissolved in water, in which case then it becomes carbonic acid. So looking at binary acid nomenclature, if hydrogen is bonded to a group 6 or 7 element, excluding water, we name it as the name hydro, the root of the element, and then ic acid. So for instance, HCl. The root of the element is chlorine, so we're always using the anion in this case, or what would be the anion if it was ionic. So we use the chlorine root is chlor. We put hydro, chlor, and then ic acid, so hydrochloric acid. The element root for phosphorus and sulfur are different from how they are in ionic substances. So instead of being SULF, sulf, like it was in ionic, it becomes sulfur. Instead of phosp, like it was in ionic, it is phosphor. So we would have hydrosulfuric acid and hydrophosphoric acid if we were using those. H2S is hydrosulfuric acid. Oxyacids, or oxacids, are acids formed as ternary acids from our oxyanions. Just like the oxyanions, they have family names that are based on the parent. The way that they are named is just like it is for the oxyanion, except that the suffix ate becomes ic acid, and the suffix ite becomes ous, for us acid. So for example, chloric acid would be the acid formed from the chlorate ion. Again, the root of phosp and sulfur are the same as they were in binary acids. So we have phosphoric acid and sulfuric acid. We do not use the prefix hydro when talking about oxacids, so be careful with this because we can have sulfuric acid and hydrosulfuric acid. Those are two different things. They follow the same family pattern as oxyanions do, where adding an oxygen would be per, and then the root, and then instead of ic acid, so instead of chloric acid, HClO3, HClO4 would be perchloric acid. If we lose an oxygen, we have the root, OUS, and then the acid. So instead of chloric acid, we'd have chlorous acid. If I lose 2 oxygens, then it's hypo, the root, and then us acid, so hypochlorous acid. Now, acid salts are ternary ionic substances which are derived from an oxyacid reaction with a base. So for instance, sodium hydroxide reacting with phosphoric acid would produce sodium phosphate in water. If I do not complete the reaction, then hydrogen is left behind in the molecule. So for instance, if I react each H3PO4 with only 1 sodium hydroxide, I'll get sodium dihydrogen phosphate, so 2 hydrogens left behind. This is called an acid salt. Naming acid salts is like an ionic substance, except the word hydrogen is inserted between the metal and the anion. So for instance, instead of sodium phosphate, we would have sodium hydrogen phosphate in the case of having 1 hydrogen stuck in there. If we have more than 1 hydrogen stuck in, we'll use a prefix like di on the hydrogen. So instead of just hydrogen, it would be dihydrogen. For example, sodium dihydrogen phosphate would be just like sodium hydrogen phosphate, except there will be 1 sodium and 2 hydrogens instead of 2 sodiums and 1 hydrogen. The prefix hydrogen is often used in archaic nomenclature as bi. So instead of having something like sodium hydrogen phosphate, we would have sodium biphosphate in older nomenclature. This is where the term sodium bicarbonate comes from, what we know as baking soda. Sodium bicarbonate, NaHCO3.